All right, let's get right into it. We're talking about Advanced Driver Assistance Systems, or ADAS. Specifically, we're diving deep into a procedure where close enough is a recipe for disaster. We're talking about radar calibration, where precision isn't just some goal, it is everything. This is a non-negotiable, absolutely critical process.
Think about this for a second. What is the actual difference between a car's safety system working perfectly and a total disaster? I mean, when you're hurtling down the highway, the systems that are supposed to protect you, things like automatic emergency braking, they need perfect information. So what's the line between a safe trip and a catastrophic failure? You might be surprised.
Believe it or not, sometimes it's just a single degree. That's it, 1 degree of misalignment. It sounds like nothing, right? I mean, it's an impossibly small measurement. But in the world of radar physics, that tiny, tiny error, well, it has absolutely massive consequences. So let's break down exactly why.
So, this is really a game of millimeters, and it's all about the physics of failure. To really get it, you have to picture how the radar sensor sees the world. It's not like our eyes. It shoots out this cone-shaped beam of radio waves. And just like the beam from a flashlight, the further out that cone goes, the wider it gets. So a tiny little error in the angle right at the bumper, it gets magnified exponentially the further down the road you look.
And here is where it gets scary. A 1-degree error. Just one. That can mean your car's system completely misses an entire vehicle 100 meters away. That's about the length of a football field. Think about what that means. A 1-degree error sounds so trivial, but at that distance, your radar beam is literally pointing at the wrong lane. The car that's directly in front of you, it's basically invisible to the system that's supposed to be protecting you. We're not talking about a minor glitch here. This is a total, complete failure of the safety net.
Okay, so when do you actually need to worry about this? When is this calibration required? Well, it's not just after a big crash. No way. Even a minor little tap in a parking lot could be enough to throw that sensor off. If you do any front-end work, messing with the bumper or the grille, you gotta do it. If you replace the radar module itself, obviously. But here's one people forget. If you modify the vehicle's ride height, like with a lift kit or new suspension, yep, that requires it too. Even some software updates can trigger the need for a full recalibration. It's all about making sure that 1-degree error never, ever creeps in.
But listen, getting the angle right, that's only half the battle. There's another huge factor here, the environment, the actual space where you do the calibration. Because the sensor can be tricked, fooled by invisible enemies right there in the shop. You could think you did a perfect job, but you've actually created a system that's doomed to fail out in the real world.
And the number one enemy has a name: Multipath. The easiest way to think about it is like an echo, but for radar. Okay, so the radar sends out a pulse, and it's listening for that pulse to bounce directly off the target and come straight back. Simple enough, right? But what if that pulse also bounces off a nearby metal wall, then hits the target, and then comes back? The sensor gets all these confusing, delayed signals, and what happens? It starts seeing things that aren't there. We call them ghosts or false targets.
And you know what? These sources of interference are everywhere in a typical shop. We're talking about metal storage racks, big toolboxes, those overhead metallic beams, or even a chain link fence. Heck, even having another vehicle parked too close can create these radar echoes. This is why the calibration environment has to be, and I mean has to be, a sterile, controlled space. You've got to clear out all that metallic clutter. If you don't, the calibration is just fundamentally flawed right from the get-go.
So that brings us to the actual procedure, and I want you to think of this less like a task and more like a strict methodical ritual. Seriously, every single step has to be done perfectly because each one builds on the last. You make one mistake in the prep work and you've guaranteed a failure in the final result. It's that simple. So step 1 is all about prep. Think of it like a pilot's pre-flight checklist for both the car and the workspace. We're talking about every little variable that could affect the car's orientation. Is the floor perfectly level? You have to check. Are the tire pressures exactly where they need to be? You have to check and correct them. Is the sensor itself spotless? Is the area clear of all that metallic interference we just talked about? Is the steering wheel locked dead straight? Every single one of these items is a non-negotiable. You can't skip a single. And you're not going to be doing this with a standard set of wrenches either. Performing this ritual requires highly specialized equipment. You need the manufacturer-approved radar target board, a really precise adjustable stand, specific calibration fixtures like a corner reflector, and of course your measurement tools and a diagnostic scan tool that can actually talk to the car's ADAS module. Let me be clear, using the wrong equipment is just as bad as doing the procedure wrong. There's no room for shortcuts here. All right, so the vehicle is prepped, the workspace is sterile. Now we can finally move on to the alignment itself. This is where the physical, mechanical precision meets the digital side of things. It's a delicate dance of measurements and software.
Now, this procedure demands that you follow the manufacturer's specs to the letter. There's no guesswork. The target has to be placed at an exact distance. It has to be centered on the car's center line down to the millimeter. The height, the orientation, everything has to be perfect. Only when all of that is set up just right can you plug in the scan tool and start the calibration. This is the moment the radar learns its exact position and sets that all-important baseline for what it's going to see on the road.
So you've done all that meticulous work. You followed every step. You must be done, right? Nope, not even close. Because a successful calibration in the controlled environment of a workshop means absolutely nothing until it's been proven to work where it counts, out on the road.
The proof is in the pudding, as they say, but here, the proof is on the road. The functional test drive isn't just a good idea. It's the ultimate judgment. It's the final exam for your work. This is the only way to know for sure that the adaptive cruise control is holding the right distance, that the collision warnings are working exactly as they should. This is what confirms that all that preparation, all that precision, resulted in a system you can actually trust with someone's life.
So what happens when things go wrong? Well, failure almost always points back to a flaw somewhere in the process. If you keep getting misalignment codes, you probably messed up a measurement, or maybe the mounting bracket itself is damaged. If the car is seeing ghost objects, well, that points directly back to that multipath interference we talked about earlier. See, success isn't just about knowing the steps, it's about understanding this whole ecosystem of potential failures.
So, when you boil it all down, it comes back to this one idea. Proper radar alignment. It's so much more than just bolting a sensor on a car. It is a genuine commitment to safety. It's a discipline where every single millimeter matters. The margin for error is zero, because at the end of the day, that single degree, that one tiny millimeter, that really is the difference between safety and disaster.